All right, chem students, today we're going to be talking about limiting reactant. In a chemical reaction, one of the reactants will usually run out before the other reactants. At this point, the reaction will stop because one of the reactants has been completely used up. The reactant that is used up first is called the limiting reactant. It controls how much of the other reactants you will need, and it also controls the amount of product you can make. The other reactant is called the excess reactant because there will be some of it left over. Now, a great example of this would be making grilled cheese sandwiches. If you're given 10 pieces of cheese and 50 pieces of bread, and the equation for making grilled cheese sandwiches below, 1 piece of cheese plus 2 pieces of bread, add some heat, and you have a cheese sandwich, how many complete grilled cheese sandwiches could you make? Well, the correct answer is 10. Okay, so what would be our limiting reactant? That would be the cheese. We would run out of cheese first, and that would make the excess reactant the bread. So how many pieces of the excess reactant would we actually use? Well, if we had 10 pieces of cheese, and if we needed 1 cheese for every 2 breads, we would need a total of 20 breads. So 20. Now, how many pieces of the excess reactant would be left over? Remember, we started with 50, and then we used 20. So 50 minus 20 means we had 30 pieces of bread left over, or 30 of our excess reactant. Okay, now let's use that same concept in a chemical reaction. If we have 2 aluminums reacting with 3 copper chlorides, that will give us 3 coppers and 2 aluminum chlorides. Now, we're going to assume that the copper 2 chloride, is the limiting reactant. Which substances would be present in the reaction container once that reaction had completely stopped? So think about it. If this one is used up, what would be left over? Well, the answer would be everything but the limiting reactant. This one is gone. It's used up. So we still have some leftover aluminum that never reacted, plus all the products that we made before the limiting reactant ran out. So everything but the limiting reactant would be present. Now think about this. What kind of reaction is this up here? The answer would be single replacement. Okay, so in basic stoichiometry problems, you are provided with only one given quantity. In a limiting reactant problem, you are provided with amounts for both reactants. Before you can solve the stoichiometry problem, you have to figure out which of those 2 reactants is your limiting reactant. The limiting reactant is used as the given quantity in all calculations after that, because it controls the amount of the other reactants used and products made. It is possible to have the 2 reactants run out at the same time. And if this happens, the amounts of reactants are called stoichiometric amounts. In that special case, it means there are exactly the same amount of each, and they both run out at the same time. All right, how to find the limiting reactant? First, we need to start with the given amount of one of the reactants. We'll call it reactant A. And we solve for the amount of one of the products that it can make. We'll call it product C. The next step would be to start with the given amount of the other reactant and solve for the same product. That's the key. You have to be able to compare it to the same product to see which one can make the least. Step 3, like I said, is the reactant that produces the least amount of product will be your limiting reactant. You can then use the limiting reactant to work any additional problems they ask. Okay, so let's practice this. We want to find the limiting reactant if 0.5 moles of each reactant are available. The first thing we got to do is balance our equation. We would need 2 calciums plus 1 molecule of oxygen to give us 2 calcium oxides. Now, we're going to start with 0.5 moles of each. It's already in moles, so we don't need to convert it. We're going to go straight to our mole-to-mole ratio. So we would need 2 moles of calcium to make 2 moles of calcium oxide. So we only have one product, so we're just going to use calcium oxide. This would work out to be 0.5 moles of calcium oxide could be made with 0.5 moles of calcium. So let's do the same thing with oxygen. If we have 0.5 moles of oxygen, we would need 1 mole of oxygen to make 2 moles of calcium oxide. So this one, with 0.5 moles of oxygen, we could make 1 mole of calcium oxide. That means this one is smaller. So whatever we started with, in this case calcium, calcium would be our limiting reactant. It would run out first. All right, let's do another example. So first we have to balance. So we would need 2 moles of aluminum, plus 3 moles of copper chloride would produce 3 moles of copper plus 2 moles of aluminum chloride. Now, let's assume we have 0.25 moles of aluminum and 0.35 moles of copper chloride. First, let's see how much, well, let's pick which one of our products we're going to use. I'm going to pick copper as the product I'm going to compare to. So 0.25 moles of aluminum, 2 moles of aluminum will make 3 moles of copper. That means I can make 0.38 moles of copper if I start with 0.25 moles of aluminum. Let's see how much copper we can make if we start with 0.35 moles of copper chloride. 3 moles of copper chloride are needed to make 3 moles of copper. So this can only make 0.35 moles of copper. Now this one would be smaller. That means that over here, the copper chloride would be my limiting reactant. Remember, you always have to compare these to the same product or it won't work. All right, let's try another practice problem. This one's already balanced. We have 6.20 grams of aluminum and 48.5 grams of copper chloride. So this time we're going to have to do step 1, which is convert this to moles. So I need the mole to mass conversion. So I have 26.982 grams of aluminum in 1 mole. And I'm going to pick copper again as the one that I compare. So we're going to see 2 moles of aluminum will make 3 moles of copper. And that tells me that if I start with 6.20 grams of aluminum, I can make 0.345 moles of copper. Now let's check our copper chloride. I'm going to use the mole to mass conversion factor to get 2 moles of copper chloride. And then I'm going to convert my mole to mole ratio to moles of copper. For this one, I can produce 0.361 moles of copper. Now, 0.345 is smaller, so it makes less. That means that this is my limiting reactant over here. So 6.20 grams of aluminum is my limiting reactant. This was a part A problem. We figured out what the limiting reactant is and the amount. We have 6.20 grams of aluminum. That would be the starting point for the other problems. So when they ask for how many grams of copper will be produced, I start with 6.20 grams of aluminum because that's my limiting reactant. I convert it to moles again, mole to mass conversion, and I use the mole to mole ratio for copper again. This time though, I'm going to convert it to grams of copper. And when I get to the end, I do the math here. It tells me I can make 21.9 grams of copper. Now, part C, they ask how many grams of the excess reactant will be used. We can figure this out too. Again, we start with our limiting reactant, 6.20 grams of aluminum. We know that's the one that's going to run out, so it's the most important. We convert it to moles of aluminum again. Now, this time, instead of converting to moles of copper, I put in how much of the excess reactant we need. So copper chloride is going to go on top. So 2 moles of aluminum needs to react with 3 moles of copper chloride. At the end, I put in the mole to mass conversion for copper chloride to see exactly how many grams of it we're going to use. Multiply across the top, divide by the bottom. We will need 46.3 grams of copper chloride. Now, if they ask you how many grams of copper chloride would be left over, this isn't as difficult as it sounds. We started with 48.5 grams of copper chloride. We used 46.3. So that means we have 2.2 grams left over. So 2.2 grams of copper chloride would be left over. Okay, so take a minute and try to do problem 18 on your own. Okay, let's see how you did. Part 1. We had 50 grams each of hydrogen and oxygen. So we have to get grams to moles. So there's our mole to mass conversion factor. And we only have one product, so we're going to use moles of hydrogen and convert to moles of H2O. I could make 24.8 moles of H2O if I started with 50 grams of hydrogen. Now I do the same thing with oxygen. 50 grams of oxygen, convert to moles, step 1. Step 2, mole to mole ratio, I will come out with only 3.13 moles of H2O. Now remember, the smaller one tells us what the limiting reactant was. That means it was oxygen. So my starting point for the next problem is going to be oxygen, 50 grams. So when they ask what mass of water can be produced from this reaction, I start with 50 grams of oxygen. I convert that to moles of oxygen. I do my mole to mole ratio again, and at the very end, I convert to what they're asking for, mass. So I need mole to grams, and I will end up with 56.3 grams of H2O. The last thing they ask, how many grams of the excess reactant would be used up? Now, 50 grams of oxygen, like I said, that was my limiting reactant. So that's my starting point for these other problems. 50 grams converted to moles of oxygen. Then we do our mole to excess reactant ratio this time. This time we want to plug in the moles of the excess reactant. Then we convert the excess reactant to grams. That tells us that we would need 6.30 grams of hydrogen. If they want to know how much would be left over, we started with 50, we used 6.3, we're left with 43.7 grams of hydrogen. Okay, that's it for today's lesson on limiting reactant. Do the corresponding practice packet pages, and we'll see you for the next video.